Hello and welcome. My name is Alex, founder and director of MPSI Technologies. This is the second episode of the Whiznium developer experience, Whiznium modeling any aspect that's fit to code. In the design phase of Whiznium, which was based on an endless flow of real-life use cases, we paid special attention to finding aspects within the projects which we had seen before in other projects. If we found an aspect that came up in variations but in similar shape in numerous projects, we decided to abstract from our various use cases, conceive a model file and base automated code generation on that model file. In this episode, we will again use the Whiznium starter kit, the 3D laser scanner, to cover various aspects, showing in parallel both model file input and the resulting source code and user interface output. Before getting into specific model files, let me show you how generally Whiznium model files work. You should think of the model files not only as the input to the Whiznium source generation, but they also represent the basic framework with relevant information about your project condensed into relatively few lines as compared to the code itself. Here you can see one of WhizniumSBE model files that is used to model relational database structure. I'm using it because it is relatively straightforward to understand. What you can see here is basically a text file with hierarchical content, where the hierarchy is established by tab indentation. I'm only using Excel for editing as it's more convenient. The blue lines represent header lines which are interpreted. Below these header lines in black, there is the actual content. For example, here I'm specifying that there should be a table called object, and underneath, under table title, I specify that in singular and plural in the available locales they should have these titles. Underneath, here is the definition of table columns. So much for giving you a rough idea of how these model files work. I would also like to hint with this example that as Whiznium stores all model files for each version as a text file, it is relatively easy to keep track of changes in the model. In this repository under Git version control, for example, I can see that between these two versions, these elements have changed. Let's look into the model files for WhizniumSBE, the Service Builders Edition first. WhizniumSBE is responsible for code that runs on embedded Linux systems or single board computers. As you can see on this slide, in total there are 8 model files which constitute the model of a WhizniumSBE application. To provide some context, let's have a look at the order in which they are supplied to WhizniumSBE. There is a predefined process where Whiznium imports and analyzes model files and complements this model information with feature generation. The first thing to be imported is deployment information, meaning which components of the project are in the end generated for which target. Global features relate to things which are universal for the entire application. The database structure is next. Complete relational databases can be modeled and they can form the basis for a large chunk of the internal workings and user interface. The basic user interface structure corresponds to the organization of cards or web browser tabs into modules. Import-export structure is a powerful tool to import XML or text bulk data to and from a database table hierarchy. The operation pack structure is not so relevant for embedded systems, but here you can define atomic compute operations to be executed on connected nodes of the target. In Whiznium, for each piece of functionality, one job or C++ class is responsible, meaning that Whiznium arranges all pieces of functionality into a well-organized structure of C++ classes, which are called jobs. For things like user interface features or database queries, these are generated automatically. However, in hardware-heavy projects, like most of embedded software projects are, this import, custom jobs, specifies which hardware access or control functionality is handled by which custom job or C++ class. With the information imported up to here, it is already possible for WhizniumSBE to derive user interface features. This would mostly be related to the relational database structure, but also the navigation screen is composed at this stage. The next import relates to custom user interface features, which are added on top of the previously generated user interface features. What I hadn't mentioned up to here is that besides an insert option, the model files also allow for retrieve, update and remove operations, so it's possible to modify what the previous steps have generated. The job tree refers to the hierarchical runtime structure of jobs. For example, there is one root jobs with multiple user or M2M session subjobs, each of which has card, then panel and query subjobs, and so on. The generated job tree also comprises fine-grained details within the jobs, such as state machines and XML data blocks, which can be sent to and received by each particular job. Custom job tree features can be imported, which are particularly useful to define exact behavior of hardware controlling jobs during operation. After executing finalized model, WhizniumSBE has all the information it needs to write or iterate the project source code tree. I would like to go back to our 3D laser scanner example and illustrate how the most relevant features in some of the model files translate into actual functionality. I will start with custom jobs. As you know, the 3D laser scanner has a turntable, a camera and 2 line lasers as hardware to control and play with. The custom jobs for this project are, starting from the closest to hardware, defined in this model file. There is one source FPGA job which handles communication with the FPGA-based subsystem, or if this is not present in the embedded Linux version, there is a Linux v4L2 source job. A third job revolves around CPU load information. You can see in the model file that here it is not only possible to define jobs on a high level, but also to add settings, XML blocks, which end up in the application's XML preferences file or persistent storage. For this example of the system information, it is basically paths. Besides the source jobs, we have actuation jobs, of which there are 3. They control camera exposure, line laser intensity, and turntable rotation. Next, there are acquisition jobs, which use the sources mentioned before to acquire and pre-process data, mainly camera image data. Finally, there are image processing jobs, 2 of which are currently implemented. One implements either the actual Harris corner detection algorithm, or for the FPGA-based implementation, it just acquires the Harris corner detection algorithm results from FPGA. For the trace algorithm, it's the same picture. For the embedded Linux version, it will try to find the left and right line laser traces using differential imaging, whereas for the FPGA-based starter kit, it will only copy the corresponding data from the FPGA as the algorithm is implemented in FPGA logic. As you can see here in the source code tree, for each job a corresponding header and implementation C++ file is generated. Moving on, I would like to show the custom job tree features model file using two examples. So, as I stated before, it is possible to be very specific when modeling the behavior of jobs, in particular hardware control jobs. First, I would like to draw your attention to the trace detection job. In the non-FPGA embedded Linux option, within the model file I can declare a state machine, which roughly, as you can see, has the states idle, ready, process, left on, left off, right on, right off, and finally done. So in this model description I can already define the behavior of the class on a high level. If you think of the algorithm, it has to switch on the left-hand side laser and wait for a new frame from the camera, which is followed by turning off the left-hand side laser or both lasers, then taking another image, after which the difference can be processed. And then the same follows for the right-hand side. In terms of source code, this will generate the corresponding enter and leave methods, as you can see here, which are left for the software designer to be implemented. It is not only the state machine itself which can be defined, but by declaring sensitivities to calls which basically are events triggered, for example, by other jobs, it is possible to define jumps between states. Another nice model feature you see here, it is possible to define locale specific messages that the class should provide to a user interface when being in a specific state. What I would like to show for this example still is the job hierarchy which is established in this part of the model file. So, our laser trace detection algorithm relies on a number of sources. Besides the laser control job, the trace detection job also has to have access to the results of the FPGA and V4L2 sources. If you look at the code, you will see that in accordance to the model, these three jobs are constructed as subjobs, which allows access to their methods. Also, this results in a clean C include structure. For the second example, I would like to focus on additional things that can be declared in the custom job tree feature model description. Namely, I will use the servo job which rotates the turntable. If you look here, there are methods which can be defined. For example, move to with a target angle as invocation parameter, then stop and turn and set angle to 0. Here we have two methods with invocation parameters, but it's also possible to define methods with return parameters or both. The methods declared here not only are mapped into C++ methods, as seen here, but they are also made available to the OPC UA and DDS namespaces. The same holds true for state variables, which in this case are current and target angles. Moving on, I would like to show examples of custom user interface features. The more hardware heavy your application is, the more you will have to define your own user interface. On the other hand, when you have lots of database table structure, this will be handled for you automatically by Whiznium. I will use the low-level access camera panel to illustrate how this works. So underneath the low-level access card, here I declare that there should be a camera panel. And then I list one after the other all controls which should be part of this panel. Starting with the caption in the header section and regularize minimize button on the side, I specify pop-ups with caption, a checkbox, a slider, and yet another slider. And also a region of custom content, which I can then as a developer fill with anything I like. In this case, it's the camera image display as HTML5 canvas control. A feature worth mentioning is that for each control it is possible to define a rule stating whether it's available or not. So for example, the exposure time is not available when auto exposure is switched on. And also an active rule, meaning enable, disable, can be declared. In the source code tree, this translates to corresponding variables within blocks that can be serialized and deserialized to and from XML. So here are the active and available rules along with slider limits. Next up, database structure. Experience shows that no matter how simple the application, it can never harm to have a database attached to a project. In most embedded projects, you have to think of it as a SQLized file-based database. For bigger projects, Whiznium also supports MySQL, MariaDB, and PostgreSQL. By default, the database contains table for user access rights management. For the 3D laser scanner project, they are complemented with a simple hierarchical structure of object groups. Within one object groups, there can be any number of objects. For any object, there can be any number of snapshots with associated result files. And each snapshot comes with a number of parameters. Declaration of the tables, along with their locale specific names and table columns, can be seen here. The relations such as 1 to n or m to n follow. In fact, there is a vast number of options available for which Whiznium is able to automatically generate a suitable user interface. Another concept worth mentioning are stubs. Or human-readable representations of records. They are declared here, and at runtime efficient UI queries can be executed as those stubs are cached. Now looking at the output. Having this database structure model file results on one hand side in a C++ database access library, where you find all the tables and their records as C++ classes. On the other hand, as you see here, there is the clickable user interface representation. Whiznium follows a strict model view controller approach, meaning that SQL databases are not accessible from the outside. Rather, they are query jobs or C++ classes which are responsible for filling each user interface list view based on the SQL database. This is an example. Finally, I would like to go briefly into the deployment information model file. So, the different output components available for Whiznium are the combined engine, which serves as the daemon, the database access library, which we just saw in the previous section, the web-based user interface, and both a C++ and Java API library, which basically includes XML serializers and deserializers. The information entered into this file mainly serves to write the correct scripts and makefiles, which are highly machine or target specific. In the Whiznium master database, paths and library locations are stored. So by putting together this model file, it is possible for Whiznium to know which build instruction to generate as output. I will skip over the other model files, as I think we've already gone through enough of information for this episode, and we still have to cover the WhizniumDBE model files. Speaking of which, let's talk WhizniumDBE or Device Builders Edition, which is responsible for writing complex FPGA and to a lesser extent MCU code. If your scope as a developer is not so much programmable logic, you can skip this section. As you can see on this slide, WhizniumDBE receives its model information via two model files, basic device description and detailed device description. The first I'm showing here, again for the 3D laser scanner use case, is the basic device description. The basic device description of WhizniumDBE reflects directly the hierarchical structure of RTL projects. This is best evidenced by looking at the model file here on the right-hand side and at the same time at the hierarchical structure in Xilinx's Vivado. You see a direct correspondence of both. Besides being able to model hierarchical structures, it is also possible to specify a type for each module. The most important types are manufacturer primitives, controllers, which are modules which you can attribute a dedicated command set to. More on that later. We have inter-module buffers which facilitate exchange of data via dual-port memory. And then there is one each module of types top and host interface. The top module helps to establish the plumbing between modules. The host interface is the endpoint for commands and buffer transfers that are triggered from the side of the host. What you can also specify in the basic device description is whether a module is based on a template. Templates can be implemented in WhizniumDBE with various levels of possible customization. The most simple templates are straight copies of unmodified VHDL code from a real file repository. Others can be customized with parameters, and it is possible to specify C++ code that is compiled into a customized WhizniumDBE executable, where the wiring of a module is adapted according to parameters, also taking into account surrounding modules. The detailed device description is, as the name indicates, an extension to the basic device description. It is imported and parsed only after basic wiring that can be derived from the basic device description has been performed by WhizniumDBE. The detailed device description on one hand reflects the pin connections which result in this case in Xilinx device constraints file. But the far bigger scope revolves around adding dedicated command sets to modules of type controller and to freely edit the typical RTL trilogy of ports, signals and processes. First, I would like to show an example of attributing command sets and what that means. So here, for example, for the laser module, which is responsible for setting the left and right hand side lane laser intensities via SPI, we can attribute a very simple command set which is called set with parameters left and right. So this is the input. The output on one hand side is a VHDL module where we can see a request acknowledge handshake in the port description. Complemented with the actual values as standard logic vectors. And on the other hand, in the auto-generated C++ library for the host, we can see that you can actually simply involve the laser set command. All the plumbing, like converting the command into bytecode, transmitting it from host to FPGA and decoding it, is part of the automated source code generation. For completeness, I should also mention that it is possible to define not only command execution for the host to FPGA connection, but also bulk data transfers can be modeled. They are coded automatically when an inter-module buffer is specified between the host interface and any other module. Let's move on to the second example. VHDL code, or generally RTL code, is known to be lengthy. By offering description of state machines with decision trees up to 4 levels, WhizniumDBE allows to model the fine-grained behavior of a state machine, including conditional jumps, in a very effective way. Here I will use the stepper motor control as an example. The 4 phases of the stepper motor have to be enabled in synchronized fashion in order to implement rotational movement, clockwise or counterclockwise. The corresponding state machine description is here. And the equivalent in VHDL looks like this. As always with Whiznium, modeling and implementation are interwoven with customizable insertion points. For example, this one defined here in the model file corresponds to this one in the implementation. So, this concludes my presentation for this episode. I'm really glad you tuned in. I sure hope you had some takeaways for your own projects. Thank you for your attention, and I hope that you will be back for one of our next episodes. If you have any questions or any requirement regarding the open source Whiznium developer tools, please feel free to reach out.